Looks like we're getting some representation. Lots from Ontario today, some from Alberta and the Atlantic provinces. Let's see. Some from the territories in the US. Thank you for filling this in. I'll just leave it for another minute or so as we wait for people to file in. So it looks like we're now coast to coast. All right, I'll just share the results of this poll so you can see where everyone's from. There you go. So you can see if you scroll a little bit, we've got representation from North America. So it's great to see that. I will also share the second poll, which is what is your occupation? So we can see who it is we are talking to today. Wait for a few more responses to come in, but it looks like we've got representation for most of the categories here, so that's great. And if you don't see your career choice listed here, go ahead and put that in the chat for us to have a look at. All right, I'll go ahead and share that so everybody can see. We have builders and developers, energy advisors, government, utilities, architects, engineers, and all sorts of people. So thank you so much for joining us. My name is Stephanie Coleman. I'm with Building Knowledge Canada. And today is part 3 of our carbon emissions 4-part series. And so thrilled to have Chris Magwood here, who's going to be speaking to us about his report and the work that he has done, particularly on housing and some of the findings that he's had. And also joining him today, and we'll be speaking later on, is Oding and Adam Wright from Building Knowledge Canada. So as I mentioned, this is a 4-part series, and so today is the 3rd of the 4 parts. I've been sending out resource emails, so if you have not received them, all of this information can be found on our website, the Building Knowledge website, and you will receive a link of that today. So next week, after today, next week's episode is with builders. And so I'm pleased to say that we have Chris will be joining us, as well as Doug from Doug Terry Homes, Roya from Minto, and Philip from Mattamy. And those will be the builders that will be joining us next week and speaking about their journey as it relates to sustainability and carbon emissions. And of course, all of this is possible by the support of Enbridge. And so we want to thank Enbridge and Susan and Michelle and team for their continued support of the building industry and sponsoring events like this so that we can communicate and educate these important topics to our industry. So I'm going to stop sharing, and Chris, I'm going to hand the microphone over to you.
Okay, great, thanks. And I will just get all of this happening here. Are we good in terms of seeing the screen?
Yes, we can see it in full view.
Okay, great. Okay, well, thanks everyone for coming again to part 3 here. A quick scan of the folks attending. Looks like there are a lot of people who were here for the last session, which is great because this one sort of picks up from where that one left off. Last time we sort of looked at, the way that we go about calculating material carbon emissions. And now we're going to sort of get into what does that look like when we start studying homes that way. So I have 4 pieces to today's presentation. There are 3 studies that we've been doing here at Builders for Climate Action. The first one is for NRCan, Achieving Real Net Zero Emission Homes. So I'll talk a bit about that study. The other 2 are still in progress, but there's enough information to report. It's kind of interesting. So the second one we'll look at is some work we're doing for the cities of Nelson and Castlegar in British Columbia, for their moving beyond just energy efficiency initiative where we've done a study of 34 homes there, looking at both the energy efficiency and the operational emissions of those buildings, along with the material carbon emissions. And that is aimed at helping those cities come up with some incentive programs and other ways that they can start to move the needle on material emissions. The third of the studies is called Embark. It's funded by the Atmospheric Fund in Toronto, and we're doing that with the folks at Passive Buildings Canada. And this is a really exciting study because we've been able to look at over 500 homes built in the last couple of years in the GTHA. So this is by far the sort of the largest study of its kind in the world. And it's very early days. We just finished entering the last house yesterday. So it's just preliminary results, but I'll share those with you too. And then one case study of an actual building up here in Peterborough at Trent University, where the client, the university, decided to really pursue low embodied carbon materials. And I'll show you how that unfolded. So a quick recap, if you weren't here last time, the way that all of these calculations happen is we find the emissions information for different building materials and products in reports called EPDs, Environmental Product Declarations. Those are an ISO standard way of reporting on emissions and making sure that the same things are being included and excluded in those reports. And then we load all of those EPD results into one of two tools. They're kind of the same tool with some slight differences. Either the MCE squared tool from Natural Resources Canada or the BEAM tool from Builders for Climate Action. Our team here sort of built both of them. They're both spreadsheet versions. They use all the same source data. You get the same answers, but there's a few differences in the sort of interface and reporting. Some studies used one and some studies used the other. So they're both there. And so what we get out of those tools is an estimate of the material carbon emissions. I want to make that really clear. This is very similar to the information you get out of an energy model or a fuel mileage report or anything like that, where we're sort of taking data that was assembled in a certain way and processing it in a certain way to get a result. It doesn't mean that any of these buildings have exactly the carbon footprint that we're ascribing to them. But what it means is that comparatively speaking, if we make swaps or make different choices in the buildings, we can see what those results will be. So for those of you who know energy modeling, you never expect the energy model to necessarily reflect exactly the consumption of the building, but that moving from double pane windows to triple pane windows has a positive impact on the amount of fuel the building will need. So think of these results in the same way. They're not absolutes, but they're close approximations that allow us to make some really important decisions. So all of the information that we're tabulating for these buildings and these studies are in the sort of cradle to gate or the product phase of life cycle assessment, which is where sort of 70 to 85% of the emissions over the whole life cycle live when you're talking about building materials. And just some caveats here on the right. We don't have an EPD for every single product. What we have is representation in every product category, but we don't know sometimes a specific brand of insulation versus another brand. What we do know is we have some representation of fiberglass, some of mineral wool, et cetera, et cetera. That the calculations are based on industry averages. So your own practices, how you frame walls and how much lumber you use might not be identical. We don't include waste factors or a whole bunch of parts of the building for which we either don't have data or for which we wouldn't be coming up with any actionable results. So right now that includes all mechanical, electrical, and plumbing, fixtures, flashing, sealants, barriers, appliance, millwork, stairs, paints. There's a bunch of the building that we're not capturing. We're not capturing transportation of the materials to a job site or emissions that happen during construction, and we're not including end-of-life emissions. We're including this really big, the kind of lion's share of the emissions that happens up front when these products are harvested and manufactured. So I'll get into the first study, which is one that we did for Natural Resources Canada. And the subtitle to the report is Embodied Carbon Scenario Analysis of the Upper Tiers of Performance in the 2020 Canadian National Building Code. So what we were looking at is, what is the relationship between moving buildings higher up the energy code? So we were looking at tiers 3, 4, and 5. We were looking at 3 different housing typologies, a bungalow, a 2-story, and a row house. And we looked at 5 different cities. So the energy models for these buildings were done by Enercan based on the climate data for those 5 cities. And then what we did was applied to each house. So Enercan provided us with a set of plans for what they consider sort of the typical bungalow, the typical 2-story, and the typical row house. And then we chose 4 different material palettes for those homes. One is that you'll see, we always color it red in the study, used high carbon materials. So this was whatever the category we were looking at, whether it was flooring, roofing, insulation. We picked materials that were at the top of the category in terms of highest emissions. Then we did a sort of moderate carbon model where we picked materials that were sort of in the mid-range. We then used, in yellow, we show the one that used the best available materials. So what was the lowest carbon option for each part of the building that we all have access to and is code compliant and available. And then the 4th model was just, we went with the lowest carbon footprint, regardless of whether the material is widely used or widely available. We know that you can build with these, but they may not always be things that are common. So here's what we found, and I'm going to use the Toronto house as an example. If you go read the study, you'll see that the things look different depending on where these buildings are located. But this is the step 3 building in Toronto using electric heat, so air source heat pumps and electric hot water heating. So for tier 3, when we applied the high carbon materials, that 2-story house had a carbon footprint of 482 kilograms of emissions per square meter, of tons of emissions. The sort of mid-range model had 122. The best available materials had net storage of 3 tons, and the best available or best possible materials stored 79 tons. And then what we did was from Enercan's energy model, we added 30 years worth of operational emissions. Remember, this is using air source heat pumps, using Ontario's electrical grid. So over 30 years, that added just over 21 tons of emissions to the carbon footprint of that building. So in the study, we talk about this metric carbon use intensity, or CUI. So up here is this would be the total carbon footprint of that building after 30 years. So if you include the materials that went into making it and then the operational energy, it's just over 500 tons. And so you'll see it's the same. The buildings were sort of made to the same level of energy efficiency. So they have the same operational emissions, regardless of the materials we used. And so what you can see is, that same emissions level attaches itself to each of these models, but because the material carbon emissions represent, in some cases, such a big proportion of that, that it's the materials that really change the carbon use intensity. So the mid-range model comes down to 143 tons. The best available materials, you can get it down to 18 tons. And in fact, the best possible model is still storing 58 tons of carbon even after you've operated the building for 30 years. So now we move this up to tier 4. So essentially what we're doing is adding insulation, right? We haven't changed anything else about the house, but in making it more energy efficient, there's no carbon footprint difference to making it more airtight because you're not really adding materials, but you're adding insulation. And so what that model shows is that for the red and the blue typology, the material carbon footprint goes up some because obviously we're adding insulation materials that have a carbon footprint. So you've kind of driven that up. We have brought down the operational emissions. So that's gone from 21 tons to just under 19 tons. But what's interesting is that, between tier 3 and tier 4, these two buildings actually have a larger carbon footprint after 30 years than they did in their tier 3 version. What you see with the yellow and the green versions here is that the carbon footprint looks better after 30 years because by adding more insulation, and in this case, the insulation is what's providing that carbon storage, we're actually bringing those figures down. And then we'll move over to tier 5, and we see kind of the exact same thing happening. The red and the blue models continue to have their material emissions go up. The operational emissions come down, but especially with the red model, it's a sort of a net loss or a net gain, I guess, of carbon emissions because of those high carbon insulation materials. And you can see the blue model is almost equal here. So, in this case, the climate's not benefiting from these changes, but the owner is by driving down the amount of fuel needed. And over on the right, the best available materials model is now a net carbon store after 30 years. And the best possible building is still storing lots and lots of carbon. So a couple things kind of, we see here, what I just pointed out, that we're actually pushing the carbon use intensity of the buildings up in the red and the blue models by adding more insulation, even though we're reducing the operational emissions. And I think this is the salient point that I'm really trying to get people to see, is that, we're trying to reduce operating emissions for a reason, and that reason is to stop driving climate change. But if we do this in an ill-considered way, our best efforts to reduce the operational impacts of the building can drive up the total carbon footprint of that building. And then, as I pointed out, we get the opposite effect if the insulation we're adding is a carbon storing insulation. We're kind of getting a win-win of add more insulation, which adds more carbon storage, which also improves the performance of the building. Whoops, here's a funny, sorry about the slides there. But in this case, this is the same building in Toronto, but now using natural gas rather than electric heat in Toronto. So maybe I'll just fill all of these in. Sorry, I didn't have a chance to review these. So over here, our tier 3 building, so the material emissions stay the same. You can sort of recognize the progression in that graph, but the operational emissions have gone up. So if we look back at the previous slide, they were around 20 and now they've gone up to 100. So, this is pointing out that not only energy efficiency, but fuel choice and the sort of carbon emissions of the fuel make a huge difference. And, again, you move the building up to tier 4 and you drive those emissions down. But in total, the carbon use intensity of these buildings shows the same things. The red and the blue models, it goes up, and the yellow and the green models, it goes down as you improve the building. And the last thing that we'll look at from this study is the Halifax version. And, this is really interesting. Those of you paying attention will notice that the scale of the graph has changed. It's the exact same red, blue, yellow, and green lines, but I've had to shrink them. because the carbon footprint of that electric heat in Nova Scotia, in Halifax, is so much higher than it is in Ontario, that a building with essentially the same level of performance, same sort of tier 3, same sets of materials, now has 480 tons of emissions associated with operating it for 30 years. And so you can see our CUI has almost doubled, and that's consistent across all the material types. And so, it's a pretty dramatic difference, despite the fact that the buildings, in terms of their construction and their performance, are very similar. And we see, a similar trend. We start driving down the operating emissions as we go up the energy code tiers, to the point where we're getting close to halving it by getting that building to tier 5. But if you look between the Toronto example and this example, what you clearly see is that when the electricity source is relatively emissions intensive, like it is in Halifax, that's the best place we need to intervene. We need to get those buildings onto clean energy, because the operating emissions over 30 years really, start to outweigh the materials, whereas in Toronto, the materials really outweighed the operating emissions. And I think, that's one of the key things that came out of this study is to say, like, this is the number we need to care about, this CUI number, and we need to drive it down in whatever way makes sense regionally. So in a place like Ontario, or the results were similar for BC, they were similar for Quebec, if you're dealing with relatively clean electricity and you can electrify those buildings, then our real focus needs to be on the materials. If you're in Halifax and you, or somewhere else that's still using a lot of coal or other fossil fuels to generate that electricity, then you want to look at driving the energy efficiency of the building higher, but also working at getting the actual energy source to be a lot cleaner. And so this is just a really quick look. You'll have access to these slides, so don't feel like you have to take this all in, but this is the top 10 emitting materials for each of the buildings in that Toronto example. So you can see that which of the things were kind of driving the carbon footprint of the building high. And as we sort of move to more moderate levels of emissions, the material palette changes. It changes again here for the best available materials, where the negative numbers, all that carbon storage, comes from cellulose insulation in the roof and walls and wood fiberboard insulation as the continuous exterior. And then when we look at the sort of best possible model, the storage is coming from cellulose in the roof and straw bales in the walls as insulation. So that was, there's lots more. I would encourage you to check out the Enercan study. You can download it from Enercan's website or from the Builders for Climate Action website. There was lots more that we explored there that we don't have time to cover here. The report or the work we're doing for Nelson and Castlegar, it's not quite complete yet, but we do have all the results, so I can share those. So we looked at 34 homes, which is out of the total of 72 built in the region in that year. So it's a pretty good sample size. It's almost half of everything that got built. And it broke down into the categories you can see there in terms of housing typologies, which was a pretty good reflection of the numbers and types of buildings that get built in that municipality. So what we found from this study is that of the homes that we looked at, the material carbon emissions, the average was 26.4 tons. We had a highest result of just over 63.5 tons. And we had that should actually say lowest, but we had a lowest result of 5.9 tons. So what was interesting is, that the average falls pretty much right in the middle of those two, but it was a really even distribution. It wasn't sort of heavily weighted to a few good ones and a few bad ones. If you look at a graph of all the results, it's almost like a straight line from the best to the worst. So there's a real distribution in terms of the overall carbon footprint of these homes. And this one was exciting for us because now we're looking at real homes, as built homes, and not models like we were in the Enercan study. So we built those models from Hot 2000 models that a local energy advisor company, 3 West, had already done for those buildings. So using that, we were able to see that the average operational emissions from those buildings was just about 1.25 tons per year. But again, there was a pretty wide distribution on either side. The highest one was almost 4.9 tons, and the lowest was 0.14 tons. So, again, it was a pretty, well, the curve wasn't quite so even. There were a lot of really low ones and a lot of really high ones. And again, it had to do with fuel source, those that were on all electricity or those that were on fossil fuels. But what, the thing that really drives home from this is that it's going to take, on average, in Nelson and Castlegar, 21 years before the average operational emissions equals the average material emissions. So for municipalities like that who are trying to drive emissions down, by 2030 and 2050 targets, what this really points out is that, you're not going to be making the kind of impact you're hoping to if you're only dealing with operational emissions. You need to be thinking about the material emissions up front as well. And in some of these cases, the ones that were on clean electricity, 12 of the homes came in around that 0.14 tons a year. So for almost half the homes in the study, it's almost going to be 100 years before their operational carbon footprint matches their material footprint. So, that makes it even more clear as we start to deal with operational emissions from a fuel source point of view and an energy efficiency point of view. It's just going to make these upfront emissions more and more critical to address. Out of the Nelson study, what we were able to do is take an average of all the materials from all the homes. And this was kind of the distribution of the sort of weighted impact. So concrete was by far the highest contributor across the study. Over 35% of all the emissions generated from all of these homes came from concrete. Insulation was the next biggest category. There's a little asterisk there because some of those insulation emissions were offset by the use of cellulose. So there's another sort of almost 4% that would have been added to that insulation category, but the cellulose that was in that category kind of acted as a negative number on that and brought the overall total down. And then you can see that that cladding and windows were pretty close to each other at just over 12%, or sorry, cladding and interior surfaces. And by interior surfaces, what we mean is flooring, wall cover, wallboard, and ceilings. So there's quite a few different materials buried in there, but they have quite a bit of, they're very similar. Windows was just a little bit behind at 11%, framing at 10%, and then roofing and structural elements were a pretty small contributor. So this was really helpful to start, honing in on where are the places where we can make a difference for a municipality like Nelson and like Castlegar. That obviously there's no point in focusing on getting people to think about the roofing. It's such a small part, but we really want to think about things like concrete, insulation, and cladding if we want to start being able to drive these emissions down. And then the last thing that we did in the Nelson study was we took the house with the highest material carbon intensity. So it had a carbon footprint of 309 kilograms of emissions per square meter of house area. And we thought, well, let's just switch out a few of those high impact materials. So, we switched out in the model the average concrete that was used for the model with a high SCM concrete. So that would be a high, in the case of Nelson, fly ash version of concrete. We changed the EPS foam insulated concrete forms to wood chip ones. We changed the wall insulation from mineral wool to cellulose, the XPS continuous insulation to wood fiberboard. We changed half of the hardwood floors to linoleum floors, and we put cellulose in the roof instead of mineral wool. And you can see we got that building, we basically halved its carbon footprint with those 6 interventions alone. And so this is not an endorsement that this is, how somebody should build, or that these are the materials that somebody should be choosing. There's obviously lots of reasons and factors that you would use to decide that. But what we wanted to show was that with, in this case, what have we got? Six material substitutions, we half the carbon footprint of the building. And so, really the point of this part of the study was just to say, we can make a big difference, and it is not that difficult to do. And if these aren't the materials that you would choose to make that difference, there are other places in the building or other materials you could use to make similar differences. And so then we did the same model again with the 309 kilograms of emissions per square meter. And this time we sort of chose from the best possible materials category. So the sub-slab insulation changed to foam glass gravel, again, the high SCM concrete. We moved now to a treated wood foundation. We used straw bale insulation in the walls. We made all the floors linoleum and cork. And again, we put cellulose in the roof. And now that building goes from 309 down to 55 kilograms of emissions per square meter. So, just trying to make the point that the interventions required to make differences here, they exist now. They're not necessarily something that everybody's going to do or make all of these choices, but by at least having this data at our fingertips, by being able to use these models, we can definitely make some big differences. And the final study is Embark. This is the one for the Toronto region. Here we're looking at 505 as-built homes, so very similar to the Nelson study, but a much larger sample with an appropriate mix of singles, semis, and townhouses to match what building numbers look like in the region. But this study does not include operational energy. We're just looking at the material footprint of the buildings. And like I said, it's early days. The early part of the new year, we'll have this report out in full. But what we know right now is that in the GTHA of everything we looked at, the best, in other words, the lowest emitting building was 115 kilograms of emissions per square meter, and the worst was 263. So it was interesting. The best was nowhere near the best of what we found in Nelson, but the worst wasn't as bad as the worst in Nelson. So kind of more of a sort of middle range in the GTHA so far. So I just wanted to put these beside each other, these results, just to sort of give you a sense that, there's a sort of picture developing here that we can start to learn from. And because these buildings are now coming from different parts of the country, looking at both model and as-built buildings, what we can see is that the range for the sort of the highest, the worst emitters, that we kind of probably overstated that in the NRCan report, because we literally chose all the highest emitting materials, and clearly that's not something that people are doing as a general practice. The highest results in Nelson and the Embark study are sort of between this 260 and this 310 mark. So that seems to be a sort of more typical high end. What's interesting here is that the mid-range average from the NRCan study was 150 kilograms of emissions per square meter, and the average in Nelson was exactly 150 kilograms, and the average in Embark is 180. So those are much closer to being aligned, and in fact, depending on how we count the square meters, in the case of Embark, that this includes garages but they're not included as part of the living area, so it drives the per square meter up a bit. If we just looked at square meter built area, Embark is like, I think 152. So, you know, this is a pretty good indication that the average lives somewhere in this 150 to sort of 160 range. But, you know, at the low end, definitely, you know, what we modeled for NRCan isn't happening all that much out in practice. In Nelson, we found the lowest result was 72 kilograms per square meter. Like I showed you in the previous slide, in Toronto, it's 115. We were directed to a home in Nelson that wasn't part of the study, but that went through the same process of measurement. And it did come out with 2 kilograms of emissions per square meter, which is exactly the best available materials rate from the NRCan study. So that was a really interesting correlation. But, you know, clearly, nothing that we've looked at so far is getting close to the sort of the best possible results we're looking at. But it is really encouraging to find that, you know, we found at least one home out there that's getting close to zero carbon footprint, built, you know, affordably and code compliantly today, and getting close to being net zero in its carbon footprint from its materials. The last thing I'm going to look at now is a building that we were involved with at Builders for Climate Action for Trent University. It's their forensic crime scene building, new construction on their campus, and they wanted to achieve a zero carbon building. So we worked with the ILFI's zero carbon certification program, which mostly focuses on the operational side. So the building has about 43 kilowatts of PV on the roof, and, you know, was designed with really great building enclosure and air tightness and everything to make sure operationally that it would be a zero carbon building. But we sort of came on board to help them do the same on the materials side. So we used the BEAM tool. So we sort of entered all the key info about the building into BEAM. And one of the things that's really great about BEAM and the MC squared tool is once you've gone through the whole spreadsheet and selected all your materials, you get this sort of review tab where, you know, per by each of the building assemblies, you can sort of see all the materials you chose, their relative carbon footprint, and your sort of your total net emissions for the whole building. So we were lucky in that Trent had already been thinking about doing this building. They already had a plan and a sort of material palette that they were going to be using for the building. So we were able to make this baseline building, you know, with pretty clear understanding of what would have happened if they hadn't started to work towards zero carbon. And what would have happened was up here in this red circle, you'll see that the building would have had about 211 tons of emissions associated with its materials. So that's a really intensive building. And we, you know, then worked with the team there using BEAM to sort of, you know, point out, you know, where we could make material swaps, where we could choose different materials. So, you know, in this case, we steered them away from the spray foam insulation and towards a mix of mineral wool bats and hemp fiber bats, and, you know, et cetera. Through all the building assemblies, you know, we were able to kind of look at what material choices could they make that would both meet their budget and be able to bring down the carbon footprint. So then we, this is the review sheet for the as-built version, and you can see that we've brought the carbon footprint of that building way down, pretty close to getting to zero when you look at a per meter squared basis. And some of those material choices included things like gravel, the foam glass gravel as the sub-slab insulation. The walls were these interesting hemp blocks from Just Biofiber in Alberta, and hemp fiber bat insulation from Quebec. And in addition to really thinking about the materials, we are also really thinking about the building enclosure. So we met passive house levels of airtightness and insulation. And in that way, the building met both the operational and materials side of being zero carbon. So kind of side by side, we ended up taking a building that was bound to have 211 tons of emissions and got it down so that it was storing just under 7 tons. And maybe not everybody in every practice and for every building is going to get to that level, but this is what's possible right now today. But if you can look at a building that's going to have over 200 tons of emissions and even get it down to 100 tons of emissions, we think there's a lot of value in sort of using these tools and making this part of the kind of overall strategy of designing and building buildings. So that's the finished building up at Trent. And that's the finish of my part of the presentation. So I can now, I think we'll hold off on Q&A until Andy and Adam have had a chance to present as well. So I will hand it over to you guys now.
Very good.
Thank you.
Chris, that was awesome. That's just, to me, it's just so startling. Like, I've seen your presentations before and you've been doing this webinar, and we read the reports, especially that report that you did with the Intercan team on the impact on the tiered codes, and just that sort of buyer beware as you move up those tiers, be careful how you're solving it.
Yeah.
So Chris, one of the things Adam has been working on here is what we're going to show you here, just take maybe 10 minutes. Adam's going to walk you through some items. Is Chris is in the BEAM report, and you have the Intercan Hot 2000 tool, and you've got all these really cool metrics coming out there. And one of the things that we're trying to figure out at Building Knowledge, Adam and Steph and team, is how do we translate some of this for builders? So here's the scenario. We have builder developer clients being asked by stakeholders, whether it's municipalities or whether it's the builder's own altruistic view towards carbon reduction. They're being asked, can you reduce the amount of carbon emitted? And sometimes it's done through, community energy plans or green development standards, where they want, 30% energy reduction or 50% energy reduction, or net zero or passive house or Energy Star. But really what they're wanting is carbon emissions reduction. That's really ultimately the goal. And what we're finding is, to Chris's point, is that when you try to reduce operational emissions, we're getting to the thin edge of a wedge. So just balancing this out based on energy savings or cost savings is pretty difficult. So we've been asked recently by some builders, developers, listen, we have projects coming out. The municipality, the stakeholders, our owners are wanting to reduce the total carbon of the home we are going to build, or the homes we are going to build. So they're trying to figure out, how do we make decisions whether we do operational reduction or whether we do embodied carbon reduction. And we need something that we can just look at and make a quick decision. So Adam, if you want to start us off and sort of show them what you've developed. I think the message here, folks, is that there are other companies that are going to be able to use Chris's tools and the results of these studies to start to help the building and development community. So.
Well, thank you, Andy. That was a great little introduction to some of the work that we've been doing. So I'll just give it a little brief introduction here. So in the real estate industry, sustainability has commonly taken the form of improving operational efficiency in buildings with the focus on energy usage reductions. However, what we have learned is that the operational emissions of a building is only part of the overall emissions. So when applying the embodied carbon to a project, it is often referred to as the carbon emissions attributed to the manufacturing and the transportation of materials to the site of construction. So in this image, what you're looking at here is the entire building life cycle. And this chart is outlining how we isolate the individual emissions and break them down into the respective operational carbon and material carbon emissions. Focusing directly on the embodied carbon, we're looking at only the raw material supply and the manufacturing process of the construction materials builders are using. So buildings themselves can account for 39% of the global greenhouse gas emissions, where 28% are coming from the operations and 11% is coming from the embodied carbon. In some cases, though, this is where the embodied carbon can account for much as half of the building's total carbon footprint over its lifetime. And this is in large part due to the carbon-intensive material manufacturing processes and large quantities of fossil fuels used before materials even reach the construction site. So our initiative in this project was to provide a simple pathway for the developers to reduce their embodied carbon impact through smart material choices and applying these tools towards future construction. The tools enable us to measure and manage the amount of embodied carbon that were associated with the building materials and then choose lower carbon material options. And what we have found so far is that by simply asking suppliers for the low carbon options, we've been able to procure materials that meet our reduction targets and performance specifications with zero to minimal cost premiums. So whether it is redeveloping an existing house or if you're building new, providing a design pathway can allow the builders to see the individual impacts of the material choices, and they provide similar low carbon product alternatives that can be implemented. So by starting with the design process, we are actively beginning a greener method to approaching construction and considering low carbon structural materials such as green concrete, recycled steel, mass timber framing, and many others. We can make a huge impact on reducing the total tonnage of the carbon that's emitted. This also encourages the use of fewer materials in the buildings, and it can bring to light areas where the repurposed materials can be substituted and ultimately reduce the developmental costs. So unlike operational carbon, embodied carbon can't be reduced in materials once a building's construction is completed. So as buildings continue to improve operational efficiency, embodied carbon will become a larger portion of the building's overall lifetime emissions. And although awareness of this topic is still growing, understanding and applying the embodied carbon is a necessary step to mitigate climate change. Regulations are coming, with that being said. So as more cities are committing to decarbonization, and because buildings are such a significant contributor to emissions, it is expected that the climate action plans will limit both operational and embodied carbon. So staying ahead of this policy curve and adopting low embodied carbon practices now protects firms from the challenges and the cost of transitioning in the future. Because once a carbon tax is passed, developers will have a strong financial incentive to take action and reduce embodied carbon. So this is how BKC can help. Our tool can evaluate multiple building envelopes while comparing hundreds of EPDs from the NRCan calculator and Beam tool, where we can find the best possible products and performance results of the home. And our report can condense this material into the material data that's a readable format, and observations, improvements, and any comparisons can be made between the two in order to select the best possible design. So I'll pass it back on to Andy now, where you can talk about the report a little bit.
Yeah, thanks, Adam. So basically what we've done is we're trying to develop a report that uses both the tools of what Chris has created, the Beam tool and the NRCan tool, to give a builder a picture, an image of what the house, the impact on the home. So for instance, we want to look at evaluating each new home type. Oh, if we can just go back there real quick, Adam. If we can evaluate each new home type, whether it's a single detached, an attached home, or a MURB, what we're doing is we've set a simple metric where we look at the upfront embodied carbon, which is what Chris has been talking to us about. And then we look at the operational carbon, but we look at a 50-year lifespan. Now, we get it, 50 years is way too long. We have a climate emergency. We need to do things sooner. The reason we've chosen 50-year lifespan is because the National Building Code of Canada for Part 9 low-rise housing, 50 years is the approximate assumed lifespan of a low-rise residential product. So as a builder, developer, designer, when you build that asset, the expectation is it is going to have a 50-year lifespan. Now, we understand when it comes to operational that there's a lot of other things that are going to come into play. You know, down the road, if 50 years out, folks, hopefully we have incredibly clean grids with fusion and all sorts of things. But for now, we're building an asset. So what we're doing is we're showing the total 50-year footprint of the upfront embodied carbon plus the total footprint of the operational carbon reduction. So again, we look at these things. And from a developer, designer, builder standpoint, we need to know when it comes to reducing carbon emissions, do I look at air source heat pumps, or do I look at air tightness? Or do I look at low or neutral carbon materials? Where do I start to make an impact in designing and developing this aspect? So go ahead, next slide, Adam. So what you have here is, again, using the tools that Chris and Sona developed, is you would have for this single detached home, you would have a tons of operational carbon emission over a 50-year lifespan. And again, we can look at 20, we can look at 30, but let's use the National Building Code. We have a total projected operational carbon of 165 tons of emission. We have an upfront embodied carbon total of 59. And again, when you bring those totals together, you have, again, you want to, the total lifespan carbon emissions then becomes 224. In the graph below that, you know, we can provide the total emissions density kilogram per meter squared, but really the big number that we're trying to look at is this number here, which is the operational plus the embodied at a 50-year picture. Next one, Adam. So you can see here, this is a comparison that Adam gave. This is basically a building code based home using building code based products. And you can see that here we've actually have a total lifespan carbon reduction going from 224 down to 199. Next slide. Next fly-in. There you go. And so now we have a 15%, oops, back one, a 15% reduction in carbon, and we haven't even touched the operational side yet. And this is just simply from a small change to, let's say, the concrete going to a 25 or 30% SCM or something like that. Go ahead, Adam. So you can pick that one up.
So yeah, this is definitely why it's so important to focus on the materials that matter and to have the right data when doing so. So if nothing is done to reduce our embodied carbon in buildings, it is highly unlikely that the emissions target necessary to keep global warming within 2 degrees will be met. So with the use of these low carbon analysis tools, we can now identify the hotspots that are in the building where improvements can be made, and the team can likely find an opportunity to reduce this embodied carbon through smarter design, all without a rise in the cost. This outcome requires a focus on the material carbon in the project from very early stages and a willingness from the developer to ask the right questions to the contractors. And perhaps the most compelling feature of the embodied carbon reductions in real estate is the potential for significant progress without much upfront green premiums.
So one of the things that that Adam has done as part of this report that would be available for every product type is you can start to look at what are the opportunities. So here are active operational carbon comparisons. So for this home, if you were to go from natural gas to, let's say, an electric or a dual fuel based system, over 50 years, you could see 115 tons of carbon reduction. That's pretty substantial. If you were to go from a furnace and air conditioner straight to an air source heat pump, you could see 125 tons over a 50-year span. Domestic hot water, if you were to move from a gas to an electric over 50 years, it's 25 tons. Go to that next slide, Adam. What is the impact like for other changes? So when you look at the envelope, for instance, so how do we reduce carbon emissions with envelope solutions? Well, here's the thing we have to be careful of. We could pay a lot more to do R80 in the attic. We could go double the price, reduce the R value in half. But over 50 years, it's only 5 tons of reduction with CO2. Now, we understand there's other reasons you may want to do this, resiliency or comfort or things like that. However, in the grand scheme of things, how does it compare to embodied carbon? For instance, air tightness, again, one of the larger impactful areas, going from an already 3.5 home to a 1.5, just a very simple change there is a 35-ton reduction over 50 years. Adding exterior insulation, again, to this house was a 65-ton reduction over 50 years. Now, this changes house by house. Adam runs a multi-unit residential building. All of a sudden, air tightness is huge, and adding exterior insulation may not be as impactful when it comes to both operational or to embodied carbon. So it is a lot about geometry. Thanks, Adam.
Awesome. So overall, just to finish it off, I would just suggest using the concept of greener concrete mixes, looking for the low carbon XPS installations, installation values that have low carbon blowing agents, and switching from an HFC to an HFO agent that for putting in the insulation values. So we can make huge impacts on carbon emissions with minimal changes. And we leave it up to the developers now to implement these and try to make a change for the environment.
Sweet. So yeah, that's just Adam's information. We've been asked quite a bit lately to do some total carbon emissions reviews of product types. So we're glad to help. Obviously, there's access to Chris's tool and the work that he does, access to the Intercan tool through energy advisors and others. I'll be glad to help with that. Adam, I want you to go back just a slide quick, because I think there's something that really aligns and it's important to focus on here, because Chris hit this point too. There are some pretty simple low-hanging fruit that can make a significant impact on lowering carbon emissions, and it doesn't take much. You know, SCM, we recently, Adam and I are recently working with a sizable developer. They've been in conversation with their concrete supplier, and for a 20 to 30% reduction in Portland, or with using an SCM type of cement or admixtures, it was a no-cost change. And the manufacturer actually is able to adjust those mixes seasonally, because we know that high SCM concretes, for instance, don't have the high temperature rise, so it affects the curing rate, but they're able to make this work for little to no cost. HFO, closed cell spray foams, blowing agents, we are seeing some very substantial changes to some traditional foam type insulations where they are showing a significant reduction in that embodied carbon. So I love that point that both of you would make, is there are some pretty simple things that we can do up front pretty quickly. We just have to know what the numbers are.
Yeah, I love that you brought air tightness into it, because that's one of those ones, you know, when I did my very first report on this, I had a whole chapter on air tightness, because it's like a no embodied carbon improvement that drops the operating emissions hugely. It's like it's sort of like no investment in materials, because you're already putting those materials in the building. You're already using those barriers. It's just, if you do a better job, you know, you haven't used any more material, but you've made these huge savings. And I think I'm really glad you put that in there, because that's, you know, I'm so focused on the materials often that, you know, that's something that comes out of those energy modeling programs, where it's like, yeah, we have to make these buildings more airtight, and it doesn't require more materials to do that. And it's one of the best sort of no impact ways to make big improvements.
Yeah, that's pretty neat. Good.
All right. Well, thank you so much, Chris, Andy, and Adam. So we do have a few questions, but I'm going to start with the first question. I know I'd asked you this last week, but if anybody's new on this week, we could get some clarification. So we have a number of industry leaders who are spending a lot of money on research and development to improve products, reduce carbon emissions, and some that kind of off the top of my head are like Owens Corning, you know, with various insulations. They're coming out with some new innovative products, and we've got concrete companies, I believe Lafarge maybe. And so these different companies that are coming out with these new technologies. And so what I was wondering if you could answer for the audience is, as you get more EPDs from these companies, as they launch these new products, what is the frequency, or what is the plan for updating the MCE squared tool to incorporate these new products and materials? Yeah,
probably quite frequently, because there are sort of more and more EPDs coming. So, you know, the tools both of them are about to go out to the public towards the end of this year. And so I would imagine, you know, with Enercan, we've already talked about sort of a 6-month update. So I would say for a while, we'll kind of be on every 6 months, you know, cycle of doing that. But both tools also have a place where, you know, if somebody on the project team knows of a product and has the EPD for it, you can custom enter those things, into the software already. So if you have something you want to use, but it's not in there, but you have the info, you'll be able to put it in yourself.
Perfect. So you can manually enter it in to account for that. So that is an option if it's not already been built in, or it's brand new between that 6-month cycle. Okay, perfect. That's great. Okay, thank you so much. So we do have a couple of questions here. So the first one that came in is BEAM or MCEE, so MC squared, available to the public yet?
No, but they're both very close. My last conversation with Enercan is sort of like end of November, so really soon, and BEAM will be in January. So within a few weeks to a few months, both of them will be out there.
Okay, that's excellent. Yeah, so just right around the corner then.
Yeah.
Okay, so is it possible to get the high MCI home slide by category breakdown rather than just the totals?
I would say go to the Enercan report. The appendices have like everything broken down in big detail. So grab that report and flip to the back and you'll see everything.
Okay, perfect. Yeah, that's right. It's all in there. So what I'll do is after I get the recording links that Zoom generates and Chris's slide, will send you the resource email, and I'll also include a link to that report so it's easily accessible for everybody. Okay, thank you. Another question that came in is, what kind of manufacturers are you using for these low embodied carbon buildings? Is there hunger for more people that are actually building these components? And it's a multi question here. What are some obstacles are you seeing these companies facing, such as supply chain, raw materials, and that sort of thing?
Yeah. I mean, that's a big question, and none of us are material manufacturers, so but all of the things in the best available materials models that I've made already exist. So these aren't things that have to come into being. You can get cellulose insulation all across the country. Wood fiberboard might be a little harder to get, but there is one Canadian manufacturer and several European ones that are represented. Some of the other options, like the flooring options, we made that model specifically to say, you can go to the store and get this stuff, and it's already recognized in the code. So I don't think there are any hurdles there. The best possible materials one is where those hurdles exist, and it's like any manufacturing. You have to figure out, is there enough demand to make the investment, and figure all of that stuff out. What I'm really hoping is that generally Canadians will see this as a win-win-win kind of opportunity, where it's like, we have all the raw materials in the country to make all of these products. We want more manufacturing jobs, and we want our buildings to have a lower carbon footprint. So, the right investments now will kind of kickstart not just better carbon results, but a whole sort of like economic chain that will be sort of beneficial to everybody. So, even if climate change and carbon isn't your driving factor, if you just care about the economy, why not take cheap or free raw materials that already exist and turn them into products and sell them? It seems like there's sort of a great opportunity there for the whole country to really think about that as a strategy.
That's a really great point, because that really is the essence of sustainability and the concept of the triple bottom line, where you've got jobs. So on the social side or the people side, you've got the environmental benefits, and then also the economic or the business benefits. So that's a really great recommendation. There was a couple of questions that came in regarding BEAM. So does BEAM provide recommendations for materials to improve the net carbon footprint, or is that something the builder or EA needs to know?
The way we structured it for both BEAM and MCE squared is that in each of the material categories, so as you're kind of building up your assemblies, we put all the materials that could work in that part of the assembly side by side. So, we're not telling you which material to do, but we're showing you the carbon results for all of them. So if there's 20 different kinds of insulation and you need 100 square meters at R20, you put all of that info in and you will see the carbon footprint of all 20 insulation options. So we're not going to say to you, hey, pick that one. But by showing you the numbers, we're showing you the kind of relative impact you could have by, picking, one over the other. So it's kind of, there's some implicit, advice being given, because if you're trying to get the lowest possible number, there it is. If you want a mid-range number, there it is. But by seeing all of the numbers right up front as you're making your choices, you get to decide what it is you're trying to achieve.
So it really reinforces the importance for manufacturers to get on board, to get their products even listed on the tool in the first place, right?
Yeah, it really is, because we haven't really talked about that here, but the amount of information we have right now is pretty good at helping you pick like between different types of materials. Mm-hmm. But what we're starting to see is that even within the same category, one manufacturer could have twice the carbon footprint of the other one. You go to the store, the product looks the same, it's the same, exact same kind of material, but company A is making it way cleaner than company B. And what we're hoping is that as more EPDs come out, you're not just choosing the right category, you're now choosing, the right brand, because, you can sort of get more detailed with that information. And both tools have as much of that as currently exists. So we sort of show the average for each type of material, but where there are product specific numbers, we include those too. And it's really eye-opening. Like some of them are, vastly different than each other, despite the fact that, if you stood with them on a job site, they look and perform and cost the same. So the more HPDs we get, the better you'll be able to sort of make the right choices.
Mm-hmm, exactly. So no, that's really great points. Someone did want to know the difference between Beam and the MCE squared tool, or what any sort of differences you had between the two.
MCE squared is specifically Canadian. So where there's like specific Canadian data, we include that, and there's no US data. Beam is more US and Canada. They're the exact same, in how they function, in the answers you'll get, but the sort of range of products is a bit different. And MCE squared is on Excel, and Beam is a Google Sheets platform. But functionally, they're exactly the same.
Okay, thank you. I've got a question for Andy in here. So it says, does your analysis tool layer in home energy cost or maintenance costs, so quantitative, and or comfort to occupant, environmental impact from materials, or interior health qualitative considerations?
The answer, Lindsay, is no, it does not. That's a really good. So what you're talking about is house as a system, a tool that would actually do a full building science house as a system intersection. And no, in fact, the only tool I've seen similar to that is something that the National Research Laboratories, NRL, in the US developed a few years ago. So the tool that we have really just runs off the report, not the tool we have, the report that we have that pulls from Chris's tool simply shows the 50-year of the operational change impacts and then the upfront embodied. And then it shows the energy cost and the gigajoule rating, the energy rating. But it would be wonderful, wouldn't it, to have a tool that would show the building science intersections? Because to your point, we can't just get tunnel vision on lowering carbon. We can't get tunnel vision on lowering energy. We build homes for people to live in and quality of life. So I will throw one challenge out there to you on the building science side that is a little bit of a concern with some of the building science geeks out there, John Straub, Steve Brooks, some of these others, is we know that we need to move towards, let's say, natural-based materials. And to Chris's point, they are coming and they are there and they're good products. The thing we also have to remember is as we build with some of these materials have differing properties. Some of them may be more hydrophobic. Some of them may have a bit more propensity to be sensitive to, water exposure. So a couple of things we're going to have to be really careful of is to keep the homes healthy and durable, we're going to have to manage rainwater really, really well, better than we've ever done it before. We're going to have to Chris's point, you're not just going to make this thing airtight to lower carbon. you're going to want to lower air tightness so that you don't have any interstitial condensation in those walls. So I'll tell you what, Lindsay, if you're interested in developing a tool that does all that, come talk to Adam, Chris, and Steph and I, and let's do it.
Yeah, I was going to say that's just a little task. We should have that done in a month or so.
I love it though. That's a good point though.
Yeah, and I like to that point. We're looking at the next iteration of Beam having overlaying some of the information from the Healthy Buildings Network, where they kind of have material ratings from a sort of toxicity health point of view, and using their color coding system in Beam, so that you'll be able to kind of like see not only the carbon footprint, but if it's sort of green, yellow, red, according to the Healthy Buildings Network, that's kind of one step closer to having all of that information in one place. But it's that would be the magic tool, but there's an awful lot to figuring that out.
Well, it sounds like the challenge has been given to us. So there were a couple of questions that came in on concrete. So one was answered in the Q&A, but in case anybody missed it, I'll ask it out since we still have a bit of time. So was the concrete used in the study homes standard concrete mixes, not the new low embodied carbon mixes that are now available? Do you have data on the improvement the low embodied carbon mixes would have?
Yeah, it's a big question. And what Andy talked about earlier with the developer in the GTA getting better concrete, like there are more and more concrete EPDs coming out all the time. And actually a couple different companies have made sort of, they're kind of like instant EPDs for concrete plants to be able to make mix specific EPDs. If we look at the range of what's out there in the country right now, the EPD, this is all 25 MPa concrete, so same kind of strength characteristics. The best EPD shows 136 kilograms of emissions per cubic meter, and the worst is 690. That's a big difference, and when you phone up the ready mix company, you could be getting anywhere in that range. The Canadian average is, I think, in the 390 kilograms per cubic meter range. So, yeah, you could half the carbon footprint of your concrete with a phone call, or you could be 3 times higher than you thought you were from looking at any of these reports, because we use the average number. But if our average of 390 and you're getting 690, so understanding that and being able to start to really ask those concrete suppliers for those EPDs is huge. Like, you might find out you're doing way better than we told you you were doing, just because of the mix, or way worse. And we do, both Beam and MC Squared do include, I think about 6 different mixes. So going from no SCMs to fairly high SCMs. So you'll be able to understand a bit of that range. But if you can get an EPD straight from your batching plant, then that's ideal, because then it's not a guess anymore.
Mm-hmm. Mm-hmm. So on that, then one question came in was, how available is concrete with carbon cure add mix?
I don't know how many plants in the country have it, and to be honest, I love what carbon cure is doing. It doesn't make that big a difference right now. A carbon cure mix is maybe about 5% better than the same mix without it. And part of the reason for that is right now, carbon cure uses CO2, like manufactured CO2. So when we make CO2 gas, not by pulling it down out of the atmosphere, which would be the sort of ideal scenario, but when we sort of manufacture it, just like all of these other materials, the intensity, the emissions associated with making the CO2 eat up most of the savings of putting the CO2 in the concrete. So it's a great idea. And if we could be, say, pulling the CO2 out of the smokestack of the cement factory and putting it right back into the concrete, great. And if we're doing that with renewable energy, then it's like a 40%, 50% difference. But right now, when we're using often dirty electricity to make CO2 to put into concrete, the win isn't quite there yet. It's great technology, but the full picture hasn't developed so that we're really seeing the advantage of that.
Interesting.
But it is interesting, and it's great that, people like yourselves are thinking about this and working towards trying to resolve those, because we're certainly seeing the impacts of climate change. I know I was writing an article yesterday on the topic of mitigation and adaptation, and all while we're seeing BC just under catastrophic flooding. It's just quite remarkable. Another question that came in on EPDs is, are there any EPDs available for mainstream residential windows? They've seen high-end aluminum window EPDs, but they're looking for more kind of your everyday residential windows that builders use.
Yeah, it's interesting. Windows are another sort of hole in the data set right now. So windows are the only place in Beam and MC squared where we made the models ourselves, because only one manufacturer in all of North America has an EPD for an actual window. So what we did was we found EPDs for the glass manufacturers who supply the windows. And then we used sort of industry average EPDs for like the frame materials, whether it's wood, aluminum, fiberglass, vinyl. And we put those numbers together to give an approximation for windows, but we really need window manufacturers to start stepping up and providing those, because they're literally, of all the window manufacturers in North America, one manufacturer has one EPD for one type of product, and that's it. So whereas if you look to Europe, every window manufacturer has an EPD. So it's, it is one of the places where we really need the industry to kind of step up and start giving that data. What's interesting about windows though is that, not that they're a small part, like in the Nelson study, they were like 10-ish, 11% of the whole building emissions, but there's very little you can do about it. It's almost all in the glass. What we found was that the frame materials make next to no difference, because there's so little of that frame material, and the emissions of the difference, say, between vinyl and fiberglass and aluminum. There is one, but like you're not going to change the emissions profile of your house by moving from aluminum windows to wood windows. If you move to no windows, you'd make a difference. But as long as you're using that glass, then that's where almost all the emissions lie. One of the things that brings up is, well, you really need to weigh up whether triple pane windows are worth it, because if you're upping your glass, which we know is one of the higher things in the building, if you're upping it by a third by adding that extra pane, is that actually paying off in operational carbon footprint on the other side? That's the kind of question that Adam and Andy can answer for you is, how does that play out? Because, that is one of those areas where like you're choosing to make a carbon investment in the third pane. Does it actually, pay out in the end in terms of a lower overall carbon footprint?
We'll have to look at that. Maybe we'll pull the folks from Cardinal in there. Of course, in the building science point, to Lindsay's former point, is it might not make sense from an embodied carbon to go to a triple. However, you're going to have a window that's going to have an incredible amount of condensation on it.
Exactly. Yeah.
We see some of these double pane windows that have a surface for low E in zones 5, 6, and 7 in Canada that condense like everything. And they're low energy, but oh my, it's that building science intersection, right? It's that unintended consequence. So I really think that point you made is super important, that like no single lens works here. Like it has to be like all of them looked at, holistically to make sure that the trade-offs are we're doing the right thing for the actual building and the person in the building, versus trying to really kill it on a particular number somewhere along the line.
Yeah, it comes down to the principles of systems thinking again, right? So thinking about the three pillars, you've got your people impact, your environmental one on top of that. So that's those are really, really good points. One question that came in was regarding the commercial building that you'd presented at the end of the report. They didn't notice an account for the embodied carbon in the solar panels, and so they were wondering if that was something that had been considered.
Yes and no. I have not been able to find a single EPD from a single PV manufacturer on the planet yet. So the data isn't there. People have done sort of like academic life cycle assessments, and the numbers range a lot. Again, so much of an EPD depends on where something is being made and what the energy source is. Like making anything in a place where you're using either burning coal or using coal-fired electricity, but doing the exact same process somewhere where it's all renewables, like you're going to see a huge difference. So, that's probably going to be the big factor in PV, is where it's being made. But we don't typically include the PV because we don't include the carbon footprint of any other energy system. Like I'm not looking at what was the embodied carbon of making the nuclear plant in Ontario that's supplying the electricity,
right,
or the wires or the poles or anything. So then counting solar as this thing that you put on, itself, like you either have to look at the embodied carbon of your entire energy system or not, but you can't just say, oh, well, the solar, added this much embodied carbon, because, compare that to the embodied carbon of a new wind tower or a new natural gas plant, or, any of those things. It becomes, I don't want it to be thought of necessarily as an externality, but in these kind of calculations, we sort of have to think of it that way, because it's part of the infrastructure of the energy system, not the building itself. Mm-hmm. But I think, one thing that when we finally do see numbers for PV in terms of the emissions to make it, I think what it'll make clear is it's not worth putting them on buildings in places that already have a substantial amount of clean energy, i.e. Quebec, Ontario, BC. Yeah. Why do it? Like, you are definitely expending emissions to get the PV on your roof, and it's not offsetting any emissions anywhere else. So it's going to be a net sort of like loss, or, it's not going to work out well. However, if you're in northern Saskatchewan and you're putting PV and you're offsetting, 90% of the coal-fired electricity you would have been using, the investment in the PVs is, from a climate point of view, is going to be worthwhile. Mm-hmm. But, there's no actual numbers to sort of run that analysis. But my gut feeling is that's what we'll find, is it's not worth it if the energy system's already pretty clean.
From a carbon emission.
From a carbon point of view, yeah. Exactly. Yeah. And there's
then you get
resiliency reasons and all kinds of things that you may. I mean, I have solar on my roof in Ontario, and I made that decision for a bunch of other reasons. But from a carbon point of view, if offsetting clean electricity with clean electricity, there's no gain there for the climate.
Yeah.
Well, I would think, like from a consumer perspective, there's opportunity. As I mentioned before, I just put solar on my roof as well back in September with the intent that when my next vehicle will be an electric vehicle. So instead of filling with gas, I'll be having an electric vehicle, right? So there could be some indirect savings, I suppose, from that perspective, and then it's funded essentially by the solar panels. Andy, there was a question that came in regarding the building code, and so is there any work being done to advocate for lower embodied carbon materials to be part of the building code, or the Ontario or the national building codes?
I think that's Christina, and a really good question, and I think one on a lot of our minds of the individuals on the call today. And any advocation that you see is what you're seeing today. You're seeing Mr. Chris Magwood, who is working with parties both at the federal level and others, municipal levels, and private companies to try to figure this out. I'm not going to say there's a lot of advocacy being done other than putting a spotlight on this. Is that fair to say, Chris, at this point in time?
Yeah.
The building code that is coming, the National Tiered Building Code, the 2020 Proposed Tiered Energy Code, explicitly identifies the reduction of energy. It doesn't talk about lowering carbon, even though that's the national goal, but the development of the code at Codes Canada was explicitly to develop a tiered energy code that lowered the use of energy. There was nothing about electrification. There was nothing about lowering carbon. There was nothing at all about embodied carbon to your standpoint. That said, I will tell you that thanks to the work Chris has done, and what we are seeing in some of those circles is that there is a fast growing awareness of embodied carbon. So, you know, I guess it's up to you and to others to take what Chris has done and to start doing the advocating.
And I think we're going to...
BC has, you know, in BC, their provincial, the step code is about, I think, in 2022, introducing emissions as a factor instead of just energy. I'm not aware exactly what that looks like, but I know in the work that I've been doing for Nelson and Castlegar, they've been talking a lot about that emissions is now going to be the lens for the step code. And that the step code folks out there are, you know, circling around the work in Nelson and Castlegar, and we're about to start with Vancouver too, to kind of see how the embodied piece might play into that as well. So yeah, I think it's on the radar, but not, you know, imminently about to show up in regulation.
Yeah.
So that's really interesting. As you know, COP26 just wrapped up. And one of the outcomes from that was the acceptance, I guess you could say, that emissions need to be reduced by 45% in the next 8 years. And so when you start to think about where all emissions are coming from, that seems like a very onerous task. And so it's interesting to see that because in the work that you're doing, that what we have been focusing on, just the operational side, just is such a small part of the picture, important, but nonetheless a small part of the picture. So it'll be interesting to see. I anticipate we're going to see a lot of change coming over the next.
And what I really like about the sort of that carbon use intensity metric, where you kind of put, you know, the embodied and the operational together, you could do a CUI for 8 years. Like if we have to be 45% reduced in 8 years, get Andy and Adam to run your building, both, you know, embodied and operational, and put an 8-year bracket instead of a 50-year bracket.
I love it.
Did you meet Canada's goals? Then do better if you have. It's so straightforward. It's like, we know what the goal is, we know what the time frame is, and we know what the building's impacts are. Like, all we have to do is, you know, balance the energy efficiency, the materials, the air tightness, all that stuff, so that our CUI in 8 years is 45% less than it would have been if we didn't do any of that. Like, it's
nice.
Not that hard.
So no, that's a great idea. So I think Adam and Andy, we've got some fun calculations to work out. We're almost out of time, but we do have another question. So I want to make sure I get this one in. So what would be the recommendation for better envelope before high efficient HVAC systems? To what extent in order to reduce GHG emissions while making case studies for developers? So it sounds like what they're asking for is any sort of recommendations on the envelope before you start investing in maybe super expensive HVAC equipment.
Go ahead, Chris.
I'm gonna give the horrible, you know, answer of it depends, because it really does depend. Like, where are you? What level of energy efficiency? What cost range are we in? What are your normal material palettes? What was your energy system? What do you think of changing it to? Like, there's 15 variables in that question that it's hard to answer without knowing a bit more. But I would say, you know, what I would say is the tools are now there to make that assessment, you know, pretty clearly. And so, you know, it's a good question, but it's not there's no off the cuff answer. I think it's an answer that you want to, you know, really examine with people like Adam and Andy, who can sort of advise on what all of that looks like.
I will say, like, our experience, Chris, again, the only reason I have strong feelings on it, we've done almost 350, 400 net zero residences over the last, you know, 4 or 5 years. And looking at that, looking at the propensity to design complicated mechanical systems that are active, that have pumps, that have controls, that break down, that have, what I would say is, I would always go back to what Dr. Ted Kessick says at U of T. If you design the envelope rationally, then you can rationalize the mechanical systems. And it's just my opinion, we're not even close to rationalizing our mechanical systems yet, because we haven't got the enclosures figured out. So get your enclosures figured out, both from an energy, a comfort, a durability, a health, embodied carbon, and then figure out your mechanicals after that. And do the right type of calculations, for goodness sakes. Oh my word. Anyways, that's another, we'll do that another PowerPoint another day.
Okay, well, we just have one last question and then I'll wrap up. So someone wanted to know, and I think we answered this last time, Chris, but someone had a question about the, what is the cost to create an EPD and why is there resistance from manufacturers to provide them? Or is there resistance?
I don't know if there's resistance. I mean, you know, if you think about yourself on this call, when did you learn that EPDs existed? Like today, a week ago, a month ago? Like it's relatively, you know, I mean, they've been around for a while, but it's a relatively new thing. People are starting to ask for them, but, you know, it takes a while for a manufacturer to go, oh, like my customers, you know, want this, they're demanding this. It seems to cost somewhere in the neighborhood of like $20,000 to $30,000 to have one done. So it's not massive, but it's not insubstantial. And I don't know that there's resistance. I think there's mostly just, you know, if you're going to invest that money, you're going to want to know that it's of value to your customers. So I would say the best thing that all of us can do is everybody whose stuff you buy, write to them and say, you know, do you have an EPD? If not, I want one, or I'll stop buying your stuff. I think we'll get a lot of EPDs done that way. Yeah.
Well, that's right. And with the use of the tool, you know, getting people's products on that checklist, essentially in the MCE Squared tool is really beneficial.
Yeah.
So thank you so much, Chris, again, for a great webinar. And Andy and Adam, thank you so much for your contributions to this. Just a reminder, the next one, which is our builder panel, will be next week. And but I will send out the resource email to you this week for this particular episode. You can find all the other information in there and on our website and that sort of thing. So thanks again to Enbridge for their sponsorship. And just so you know, today, Andy's doing 2 webinars. He is up again at 1 o'clock and he is talking about air tightness, which was an important topic that we were just talking about a little bit earlier. So we'll look forward to seeing you on that webinar if you join us. And otherwise, we'll see you next week. Thank you, everybody.
Thank you.
Okay.